There is still no complete information on the damage caused. The government has asked all intelligence agencies to increase preparedness for potential disasters caused by La Nina. The La Nina phenomenon affects the intensity of rainfall and can cause floods and landslides. The La Nina phenomenon continues to affect Indonesia. On Thursday, November 4th, severe floods occurred in the vicinity of the cities of Malang and Batu in East Java province. Heavy rains caused the Brantas River to overflow its banks. Streams of water carried mud, stones and debris. Streets turned into rivers. Houses and cars were flooded with water. Authorities are conducting a rescue operation to evacuate local residents. There is still no complete information on the damage caused. The government has asked all intelligence agencies to increase preparedness for potential disasters caused by La Nina. The La Nina phenomenon affects the intensity of rainfall and can cause floods and landslides.
Welcome to the very first Water Resource Engineering campus in Indonesia. Here, Water Resource Engineering, Universitas Brawijaya, Malang.
We provide first study in water resource engineering since 1976. Our commitment established since Indonesia needs more resources for food procurement program. From these needs, irrigation feels increasingly urgent to study.
Majapahit Empire, the widest developed empire in East Java, also most of Indonesia, used one of the methods that collect rainwater in a kind of form of a sunken rectangular basin, or now we call it a pool, and used it as ritual bathing pool or as the city reservoir, the source of fresh water essential for high-density urban area, especially during the dry season. In advance, people on that era used some type of irrigation method for their farm. They streamed on a big river and alternatively streamed it into the farm. Now some of their historical heritage still exists in some place in here. From that era, we know that people are researched and smart enough to gather, optimize and use the benefit of pure water from nature. From that era, we have already studied water resources. We know that even since Empire era in Malang, Singhasari Empire, the local empire formerly a part of Malang, people already had the ability to advance process the water resources. Our people on that era used the longest and the largest river stream in Malang. We called it Brantas, the second of the longest river in Java. Brantas has the most purposes for people all over East Java, and Malang City is the source of this legendary river. Malang is a beautiful city, second largest city in East Java and surrounded by several mountains that makes Malang has so much potential. Placed of 440 to 667 meters above the sea level, makes Malang has mild climate, fresh air, abundant water resources to support Malang's agriculture that absolutely needs a lot of irrigation management by a great human resources ideas. Malang also has attractive views and absolutely living laboratories that support almost all of water resources engineering material. So here is the right place to study water resource engineering from the top to the end. Yes, we research and study more about it. Water is vital for life. We need to conserve the environment, increasing quality by the latest technology, learn and analyze changes, and spread it to people by giving education. So many water resources study to do, especially with Indonesia as maritime country. Therefore, we provide the most important study in Indonesia.
Teknik Pangeran diuntungkan dibentuk oleh para senior dari Kementerian Pekerjaan Umum menjadi satu-satunya program studi yang ada di Indonesia. Karena memang basicnya Sungai Brantas ini adalah laboratorium hidup yang ada di Indonesia ini. Suatu sungai yang sangat besar yang dikembangkan, dieksploitasi, ditata, dikelola, direncanakan, dimanage dengan baik. Sehingga jurusan pengairan mempunyai lokasi yang sangat strategis untuk kemudian menjadi barometer pengembangan teknik pengairan ke depan di Indonesia.
Choosing Universitas Brawijaya as a perfect campus to study water resources because Malang is one of the most famous education cities. Universitas Brawijaya is one of the leading campus in it. The campus that achieved world-class entrepreneurial university. 6th rank of Indonesia top university according to Kemristekdikti, the most interactive local node of 2010 Smart Campus Award, and the oldest water resources engineering in Indonesia.
Selamat datang di Universitas Brawijaya Malang, di mana Universitas Brawijaya ini memiliki 15 fakultas. Salah satu fakultasnya adalah fakultas teknik, di mana adalah salah satu jurusan yang saya kira sangat spesifik dan yang saya banggakan dari sekitar 164 program studi yang ada di UPI, yaitu jurusan teknik pengairan.
As the very first water resource engineering in Indonesia, we need to know the development of water resources study in Indonesia, a breakthrough of an institution that given water resources engineering to develop the parent project multipurpose Berantas.
Teknik pengairan adalah salah satu jurusan yang tertua ketiga di Fakultas Teknik ini, yang didirikan pada tahun 1976. Jadi berdiri karena pada saat itu sedang gencar dibangun infrastruktur bendungan di Jawa Timur, terutama di Malang ini. Dan pembangunan bendungan pada saat itu dilaksanakan semua dengan swaklola oleh para senior-senior kita di Kementerian Pekerjaan Umum, sehingga beliau merasa perlu mempunyai generasi penerus yang mumpuni. Dan dari situlah kemudian beliau meluangkan waktu di sela-sela proyek untuk membangun program studi, mendirikan dan mengembangkan kurikulum yang sesuai dengan kebutuhan pembangunan infrastruktur di Indonesia, terutama di bidang sumber daya air.
We start from a vision to become an excellent high education institution in water resources field within regional and international. An excellent central of water resource scientific society to support advanced area development and environmental perception. Also to graduate a righteous, competent, and innovative alumnus through three Dharma perguruan tinggi, scientific spirit, independent, continuous learning.
Visi misi jurusan teknik pengairan juga visi misi mengikuti visi misinya fakultas, mengikuti visi misinya Universitas Brawijaya, di mana Universitas Brawijaya memberikan visi misinya berupa bermutu dan bereputasi.
With that vision, we are truly committed, proven with quality assessment grade A by BAN PT Kemdiknas.
Jurusan pengairan sudah 3 kali mencapai akreditasi A, di mana akreditasi A adalah akreditasi paling tinggi.
Teknik pengairan ini 3 tahun berturut-turut terakreditasi A, dan yang terakhir tanpa visitasi, itu membanggakan sekali. Jadi itu. Kemudian mengapa bisa terakreditasi? Karena kondisi banyak instrumen di dalam jurusan pengairan yang memang sudah cukup baik. Contoh misalnya jumlah tenaga dosen yang berpendidikan doktor. Mungkin hampir 60-70% sudah doktor semuanya.
SDM kita adalah sekitar 34 dosen, di mana 60% dari dosen itu sudah bergelar doktor, artinya sudah S3.
Laboratoriumnya cukup bagus, sistem pembelajaran cukup bagus, manajemennya baik, dan terutama lagi adalah kehidupan di dalam kampus ini enak sekali.
Together we can grow with outstanding people to achieve our wonderful bright future in water resources engineering. We've created an excellent home to learn, contribute, and friendship. A practical environment would be the best education. We provided fascinating research labs that can be used or substituted as the real condition.
River and Swamps Laboratory.
A lab that simulates rivers and swamps can be used as practical work and research for students in the field of river engineering science and low-lying lands. A simulation for river and swamps problems and solve it by innovative solutions.
Di laboratorium sungai dan rawa ini kita fokusnya ke sungai. Sementara ini mahasiswa biasanya melakukan penelitian dari perubahan morfologi sungai, bentuk sungainya, kemudian sedimen transport di alur sungai tersebut, dan juga penanganan dari permasalahan-permasalahan yang ada di alur sungai. Jadi di situ mahasiswa nanti akan membuat percobaan dan juga penanganan pengendalian dari permasalahan sungai yang ada.
Dengan adanya laboratorium sungai dan rawa ini, kita sebagai mahasiswa dapat melihat dan mempelajari aplikasi dari morfologi sungai, rekayasa sungai, dan juga hidrolika.
Basic Hydraulics Laboratory, a simplest visual lab to study the basic of hydraulics, the open and closed hydraulics canal.
Laboratorium hidrolika dasar ini pertama tujuannya adalah untuk mempelajari perilaku aliran di saluran, baik itu di saluran terbuka, ya, flow, maupun saluran tertutup itu berupa pipa. Nah, di sini mahasiswa diajari bagaimana cara mengukur debit, melihat tekanan air, sehingga dia bisa melihat di mana kondisi aliran-aliran kritis terjadi, di mana kondisi aliran subkritis terjadi. Nah, pada perpipaan juga demikian, biasanya mahasiswa ditekankan untuk melihat kondisi aliran dalam pipa itu melihat apakah aliran itu aliran bebas atau aliran tekan, sehingga dengan harapan demikian nanti mahasiswa akan bisa melihat bahwa dengan aliran saluran tertutup itu bahwa gradien energinya bagaimana turun atau naik, apalagi kalau terjadi pada perubahan penampang.
The breathtaking lab is in here, Applied Hydraulics Laboratorium, the lab that based on history of establishing water resource engineering, an applied laboratory of hydraulics, enormous and enchanting lab that actualize learning, services, and research of all students and lecturers in this department. As facilitator of technical field development hydraulic science and technology.
Tujuan daripada laboratorium ini terutama untuk proses belajar mengajar untuk mahasiswa S1, dalam hal ini untuk praktikum model tes atau uji model fisik hidrolik. Selain itu, laboratorium ini juga ditujukan untuk riset bagi mahasiswa S1, S2, S3, dan dosen yang berhubungan dengan model tes atau uji model fisik hidrolik.
Hydrology Lab, learn and research the nature naturally. Lab that can teach hydrology cycle, rainfall, and climatology.
Di lab hidrologi ini ada beberapa kegiatan yang bisa dilakukan, antara lain untuk praktikum mahasiswa sudah dipakai untuk riset beberapa mahasiswa S2 dan S3 bahkan S1 untuk keperluan skripsi, tesis, dan disertasi. Kalau kegiatan praktikum dari mahasiswa semester 2 dan 3 itu adalah pengukuran hujan, kemudian ada evaporasi, kemudian mereka akan melakukan analisa dari hujan itu untuk intensitas hujan dan lain-lain. Kegiatan itu dilakukan biasanya kita menunggu musim hujan, tapi kalaupun tidak ada hujan maka akan dibuatkan hujan buat.
Okay, I think now it's already 11:30. Is it okay we restart our course today, Sensei?
Yeah. Okay.
Yeah. Okay.
Yes.
So
Yeah.
we have about 1 hour for the second session. Yeah. Please take this time, Sensei.
Thank you very much. Okay, so just I want to start again, and first of all, so I will make some presentation, and also after we have some discussion. Okay, just I want to summarize today's video on the sediment disasters in Taiwan. Okay. Just I want to focus on the multimodal sediment disasters. Okay. The process of multimodal sediment disasters due to Typhoon MORAKOT in the Shaolin Village, Taiwan. So as that video, this is a before, this is a Shaolin Village before Typhoon MORAKOT, taken by the DPRC, DPRC's Disaster Prevention Research Center, National Chenkun University. And this is a photo of the Shaolin Village, just at the, on the next day of the MORAKOT. This. So you already watched this situation. And also the maybe you know the this typhoon provided very heavy rainfall, but I want to show you the precipitation conditions like this. This is the rainfall depth. Rainfall depth means rainfall intensity, hourly rainfall. Okay, hourly rainfall, and this is the time, hours. Okay, time. Time, hour. This red line is for the Typhoon MORAKOT. 2009 is something like this. You know, the Taiwan have had frequently heavy typhoon. Okay, this data is for the other large typhoon. Okay, like this. Comparing the rainfall conditions with the previous rainfall, the characteristics is firstly, maybe you can understand that is very long, a long duration, okay, around 90 hours, heavy rainfall continued, okay. And also, but the rainfall intensity, hourly rainfall is not so big, not so big. For example, this one is Typhoon Kamurayagi. That is the maximum hourly rainfall reached to 140 millimeter per hour. But this time is around 550 millimeter per hour. Okay. And this is the rainfall depth. That's a cumulative precipitation. This Typhoon MORAKOT case, the maximum rainfall depth reached around more than 2,000, for 3 days, like this. And this is the distribution of the cumulative rainfall, and this area is more than 1,000 millimeter. Okay, 1,000 millimeter. And this is the most highest part. Shaolin Village is maybe something around like this, around here. Okay, like this, this rainfall has some high intensity. Okay, not too high, just high intensity, but too long duration, around 3 days. And as a result, they had the extremely large amount of rainfall volume. Okay, and also very wide area. Okay. This is the rainfall condition of this. Anyway, so too much water was supplied to the mountain area. Okay, that is triggered the deep-seated landslide. So maybe you understand. A lot of hazard happened in the Shaolin village. This is Shaolin village. So you remember some river here, main river, and there are some tributaries here, and there is some bridge. The main center of the Shaolin village is here. Okay. And actually, the much safer area is here. Much safer area. Actually, Shaolin village disappeared by the typhoon, but this area has no damage. No damage. So that means this area is much safer than this Shaolin village. Like this. Okay, and for this location, there happened many kind of some kind of hazard. One is the some debris flow, okay, from the tributaries, okay? And inundation took place. Flood inundation took place, and the flood took place, and also the deep-seated landslide took place. Okay, there are many hazards happen here. This is a photo of the deep-seated landslide. So this is a slipping surface here, slipping surface. Okay, here. Okay, so just I want to we look at the process of the multimodal hazard. Okay, this is Shaolin village, and the deep-seated landslide took took place here. Okay, and this is river, and this is the road. Okay, national road. These are the bridge here. This is a safer area, and this is the Shaolin village, and this is the evacuation place, refuge area. That is a elementary school is here. August 7th, in the early morning of the 8th August to 2009, rainfall is starting. Rainfall was becoming very strong. Okay, and I'm sorry. Sorry. This timing shows the government issued red warning alert. Okay, this timing. Okay, already. This village, the people know now they are in the red warning situation. And then rainfall is becoming much stronger, and also in the evening of August 8th, okay, around 5 p.m., cumulative precipitation is larger than 500 millimeter. Around here, inundation took place near the number 9 bridge around here. So just one local people talked. So around this time, so inundation Okay. And at that time, maybe the people are evacuated to this elementary school. Okay. But inundation is happen and they cannot evacuate to the safe area at this timing. Okay. At this timing, they cannot move to this safe area. And then 7 or 8 p.m. of this day, the debris flow ran in these tributaries. And this bridge was broken by this one. At this time, the completely impossible to evacuate this safe area. Okay, this area is isolated. Okay, and in the early morning, more severe inundation and the backflows happened here. Okay, and also the around 8 p.m. Another debris flow took place, and also this number 9 bridge also damaged. And 6:20, around 6:20, deep-seated landslide took place here, and main part of the sediment body attacked the Shaolin village directly, and the other part is blocked to the river to form the landslide dam. That is a 6:20. And 7 a.m., this landslide dam was broken, and the flow is overtopping, and this landslide dam was broken. And quickly water discharge increased to the downstream. Okay, just one gentleman told just one gentleman in the downstream, living in the 10 kilometer downstream. He said the quickly water level is decrease, and then quickly increase the water level. Maybe when the at the time of the deep-seated landslide occurrence, maybe the flood was stopped here, and in the downstream, water level is quickly decreased. Okay, maybe at this time. And sorry. And after, around 40 minutes later, this dam was broken, and in the downstream, water level is quickly increased, rising up. So that is a process of this phenomenon. Okay, maybe you can know, you can understand there are many components of multimodal hazard, multi-hazard. Okay, for example, local inundation, rockfall, small sediment runoff. These are the these are the small scale hazard. Okay, small scale hazard, not so dangerous, right? But and also the debris flows, bank erosion, flood inundation, sediment deposition, shallow landslide. These are the middle hazard. This is very small hazard. This is middle hazard, middle scale of hazard. And deep-seated landslide dams, huge flood with collapse of landslide dams. These are the very large-scale hazard. Okay? There are many components of multi-hazard, but some is very small. Some is very rather middle. Okay, some is very large. Okay, sediment disaster is due to the sediment disaster is caused by this combination, the combination of these components. Okay, combination. Maybe during heavy rainfall, so we have the sequential and simultaneous hazard pattern. There are many patterns, okay? Different pattern. We have the different pattern. Location of the hazard, timing of the occurrence, and the scale of the hazard. These are quite different, and each sediment disaster has a different combination of the hazard components. Okay. As a result, we have the different type of disasters. Different type of disaster. Anyway, so but the component is this, okay? But the combination are different, and different pattern created different disasters, right? And also we need different countermeasure for the different disasters. This is my important point for the future research. Maybe you may understand this one. Maybe you can find many kind of research topics, I think. And for the warning and evacuation system, the important is what is a key hazard in better evacuation action. When we take the evacuation action, that timing is very important. Okay, but I think there is a key hazard for the trigger of the evacuation action. Okay, so maybe we need to consider these components of the hazard. Okay. For example, this sediment disaster in Shaolin village, government issued the red warning alert here. If at this timing they evacuated this much safer area, they didn't lose their life. Okay, nobody killed. Nobody was killed. This time, inundation took place. Of course, this is a little bit dangerous time for the evacuation, but maybe possible. Maybe possible. Okay, maybe possible. But at this time, debris flow broke the bridge. That bridge was broken. This is impossible to go this area. Okay, it's too late. Okay, and also inundation, and also another debris flow, and deep sea landslide took place. Okay, completely impossible. time for evacuation, right? Looking at this process, how do you think when did they need to evacuate, right? Of course, we can say this time to this time, maybe we cannot. Okay, but if they can predict the future phenomena, okay, if they predict the future phenomena like deep sea landslide, maybe they evacuate at this time, right? If they know the, but they cannot predict the occurrence of deep sea landslide. They may stay this area, this place. Okay. Actually, this is the just the yes. So, what is a key hazard? Actually, in the Shaolin Village disaster, deep-seated landslide is not key hazard for evacuation. Okay. Maybe the key hazard is some local inundation of in the village, I think. Okay. In the first class, I introduced Typhoon Taras disasters in Kii Peninsula. Okay, and also this typhoon is strong and very long, 2 to 3 days. And we had many deep sea landslide and landslide dam. 2 years later was the Shaolin Village disaster. Okay. When we visited the Shaolin Village, we discussed the possibility of the similar disaster in Japan. At that time, maybe we will have the similar disaster. We discussed. Okay. Actually, 2 years later, we have the similar disaster like this. At that time, so do you remember that that's rainfall, hourly rainfall and cumulative rainfall is something like this. On this snake line, what kind of hazard happened? This is very important factor, information. In the Kii Peninsula disaster, and also we have the many components of multi-hazard. Local inundation, rockfall, sediment runoff, debris flow, and something. Shallow landslide, deep sea landslide, and huge flood. Okay, this is a small sediment runoff. But if we have this kind of deposition, we cannot evacuate safely. Okay, not impossible. Okay, possible, but dangerous. Right. And we investigated the what kind of hazard took place on this snake line. Result is just this is critical line for sediment disaster. Actually, the condition is coming to the right region. Some hazard happen. For example, stage 1 around here. Okay. Difficult evacuation due to small debris flows, rockfall, and local inundation. Okay, difficult evacuation, but not impossible, but difficult, not safe. And from here, stage 2, high risk of large-scale landslide and huge flood. Nobody can evacuate. And the structural countermeasure cannot work for the large-scale hazard. Okay, just we will stay there only. And the next stage 3 is high risk of deep sea landslide and huge flood by the coast. This is the most dangerous time. Okay. And then the situation is coming back here, but around here, rainfall stop, but soil water index is still large. Okay. At that time, still high risk of deep seated landslide. Rainfall is stop, but soil water index is very high. That means there are a large amount of water is included in the mountain. So the risk of the deep-seated landslide is still high. Okay, and then going to safer condition. Like this, on the snake line, situation is changing time to time. Okay, but in Japan, we have the sediment disaster information system using this one, soil water, using soil water index and maybe this one. And the government is issued warning around here. If they predict their rainfall condition is coming into here in the 1 or 2 hours, they issue the alert. Okay, that is that system. This is critical condition, and this is we are now here. We are now here, and government predicts the next 1 to 2 hours our hourly prediction. Next 2 hours prediction. If that situation is coming here, they issue the alert. That is a system, our system. Okay. But there are many patterns. Case A is snake line is here. Case B is here. Okay. And but can you predict the coming risk, or can you imagine the scenarios of disaster? So I think it's very difficult to predict and imagine. Okay, maybe in the current system, we can know the risk in next 1 to 2 hours in the area. Okay, if the situation is coming here, risk could become much higher. Okay, so we can know, but location and scale and what kind of hazard, we cannot get these information, the information on the these. Okay, location. We cannot we cannot know the location and the scale and what type. What type means the what component happen, when and where, and the scale. There is no information. But actually, on this snake line, the hazard is sequentially different hazard take place sequentially and simultaneously. Okay, but this system cannot provide this information. Okay, so we cannot imagine the scenarios of disasters. Okay, so and also the if we know the on this snake line, for example, now we have the small scale hazard. Okay, if you want to evacuate, this is the last timing. this kind of information, if the government can provide this kind of information, so the local people may evacuate, its trigger, evacuate. But now risk is high, just only this. Okay, if we know the after the critical line, now small scale of hazard will happen, and now so the risk of the large scale landslide is very high. Okay, so maybe the people never evacuate like this. So this kind of we need this kind of information, I think. And the next is just I want to say countermeasure for large scale sediment disaster. As you know, we have the structural countermeasure and the non-structural countermeasure. This is a non-structural countermeasure, right? Okay. And also this is structural countermeasure function is control sediment runoff and trap the large stone and rock fall and trap the wood debris. But for the large scale sediment disaster, they have the limitation of the effect. Okay. For the small and middle phenomena, this can work very well, but for the large scale disaster, they cannot control completely, right? But but maybe for on this snake line, structural countermeasure can work very well for this time. Okay, this is small scale hazard, but this at this time hazard could be much larger. Okay, so the structural countermeasure cannot work very well. Okay, structural countermeasure will give up. Okay, so but just the considering the timing of the evacuation. Okay, no, if without structural countermeasure, after this line, it's dangerous, difficult time. We have the difficult time for evacuation without structural countermeasure. That case, we need to evacuate at this time, before this line. But during this time, structure protect from the disaster. Okay, can work very, very well. So the people can evacuate also during this time. Okay, this point is also very important, and so we have the leading time for the evacuation, and so structural countermeasure could make the leading time for evacuation. Okay, so that means I want to say the combination of the structural countermeasure and the non-structural countermeasure is very important. Okay, just today's point of discussion is this is okay. Last class we discussed about point 1 and 2, and today just I want to discuss about point 3 or 4, and what kind of research is necessary to mitigate future huge sediment disasters, And the second point is information on the process of multi-hazard is very important in the effective warning and evacuation system. What kind of research is necessary to predict the process of multi-hazard? These are the maybe in the future research you will have for future research we want to discuss about these 2 points. And just one firstly I want to introduce my idea, okay, first, and also the research is on the prediction of rainfall condition using climate change model and the phenomena causing sediment disasters and the conditions are very essential. This is a prediction of the future rainfall conditions using climate change model. Okay. Anyway, this is very essential point. And also the numerical simulation model are quite useful to understand phenomena we've never experienced. Research on development of numerical simulation methods are indispensable as a tool for predicting future sediment disasters. And research is on feasible and effective non-structural countermeasure, and also non-structural countermeasures in cooperation with structural countermeasures will be needed in our work. And this is a combination of the both countermeasures. And to predict the process of multi-hazard, numerical simulation method is necessary. This is my idea, and we have another 20 minutes, 10 minutes or 20 minutes. Just we want to discuss about this point. Yeah, thank you very much.
Yeah, you're welcome, Fujita Sensei. Okay, ladies and gentlemen, I think it's already clear in this second session. Professor Fujita already mentioned what kind of countermeasures we should take to prevent the landslide and also to minimize the risk, as well as the he outlined also the potential research for future climate change also. So we have 20 minutes for discussing two things. First is what kind of research we should give priority, and then regarding to this also we can extend what kind of countermeasure also. And Fujita Sensei already proposed his idea regarding landslides and also sediment-related disaster research roadmap. Maybe we can take also here in our future roadmap also. So in this time also I invite maybe representative person from Lantas Basin Authority, and also from PUSDA and MSD researcher also. We can extend our collaborative research also. So do you have any idea or any support comment also? Please let us know. Monggo Bu Nuraini, please.
Good afternoon. Thank you for the opportunity. I'm here as a representative. Sorry for our leader for not joining this event. However, if we talk about the occurrence of the big flood that happened several days ago it could be related with the climate change, I think. So maybe a research that related with the rainfall event related to the climate change could be more interesting if we make a study that related with a lot of parameter, maybe dynamic parameters, such as also the how to say modeling of the surface conditions, such as the land cover. How if we make several model that related with the cover, and also of course the rainfall and some of the regulation that we have. Maybe it will be useful for us if we can develop a regulation related to the research result. I think that's. Thank you.
All right, thank you, Bu Aini. I think in the next we can start the joint research also with Professor Fujita and also other network here. Yeah, we have MSD network also here. So yeah, it's good to extend our collaborative research also. Thank you. Any more comment maybe from MSDers, Furati? You have experiences in modeling for the as Fujita Sensei outline also. How can we get information for rainfall model, global rainfall model, to predict the impact of the climate change in the future? Furati, are you there?
Yes, Pak Dian.
Yeah, please give us some comment also. Are you okay?
The global rainfall data set, you mean the real-time rainfall observation? That one we can take easily from GSMAP or TRIM, right? But in the case of future prediction of rainfall tendency, maybe we can. I don't have so much experience in climate change study because my focus is on the disaster, basically the disaster mitigation, not a really kind of extreme event. But I think for the rainfall prediction, for the future projection in the climate change context, we can get from some scenario from IPCC, I guess so. Yeah, basically for real-time observation, GSMAP is very good.
Hey, thank you, Furati. Yeah, I think this is the Fujita Sensei ideas. So the prediction of rainfall condition and using the climate change model and phenomena causing sediment disaster under the condition are very essential. So okay, maybe next we have to move not only regular or small scale of the disaster, but we have to move to the extreme phenomena also. Okay, any more comment from the Sensei?
Dian-san, this is Fujita. Regarding topic 1, okay, just my comment.
Yes.
Regarding on the topic 1, as you know, in Japan, meteorological National Institute of Meteorology, I'm not sure, but that is simulate the future rainfall conditions using the IPCC model result. Yeah, scenario, and 2-degree increase or 4-degree increase case, something like this. And they simulate a lot of pattern of the rainfall using supercomputer. And they simulate, they collected a big data for the simulation result. And also the, the Professor Nakakita group, DPRI. His group is using that output of the simulator, and then they predict the flood and sediment disaster and something like this. In Indonesia, some people, is there some researcher simulating the future rainfall condition? Is there or no? There are no.
I think there is, yeah, but we are not sure in our group here. There is a researcher who has this, who dealing this extreme event for impact of the climate change. I think Burate already visited many times to Super K laboratory. Do you have any comment, Burate? Maybe you also have some information how to get the result of the global climate change model? No? Okay.
Yes, I yes, I visited supercomputer, and I'm not sure if we can access such server for running the model, because
Yeah.
to be honest,
The
it
result, I
requires.
mean.
Yes, the
Sharing-
result.
Yep.
Yes, the result. They have so many running procedure using many data and many scenario, and many results also we can see from, I could see from their calculation. Yes, for adjusting up, just applying the, just using the result, maybe it's okay for me, maybe, yeah, because I think for running by myself for the kind of GCM model, it requires a big computational resources as well as the scripting skill, which is not so much good for me. Then I think the collaboration is important in this case.
Yeah,
Thank
I think the collaboration is very important, and because we cannot simulate. So anyway, you should collaborate with some group doing some huge simulation of future rainfall. In Japan, there are big group. Some is providing the future rainfall condition, and some considering the future flood condition using the future rainfall simulation result, and some is doing some future sediment disaster. That's a very big group. Maybe I hope so in Indonesia, if you have such a group, big group, it's very nice, I think. Yeah.
Right.
Thank you very much.
Thank you, Sensei, for the suggestion also. Yeah, let's start to initiate our research group, collaborative research group from the agencies, from the Berantas Basin River Authority, also from the PUSDA, and also universities also. We can collaborate with Polinema, with USM, Pak Jasaul, and yeah, many persons. I think we can start here. Thank you, Pak Fujita, and also other participants. Maybe we are approaching the closing sessions, yeah. But yeah, I think many things we can continue for discussing this potential research we can conduct in future. So maybe next course, yeah, next week we will continue for in detail for the discussion of this 1, 2, 3, and 4 proposed idea from Fujita Sensei. Is it okay, Fujita Sensei? Because now time is almost approaching the end of the session, following our agenda.
No problem. Next Saturday.
Yes,
next Saturday. So
next week.
So let's continue for the discussion.
Right. So next Saturday is a very important session. We will formulate what kind of research group and also the priority of the research we should conduct due to the increasing of the extreme event. So it is, I think, very important to us also. So don't miss this last course next week. Thank you, ladies and gentlemen. I think now is time to close this session. I will return back the time to Master of Ceremony. To Tian, time is yours. Thank you, Pak Fujita. Let's give us a big applause once again.
All right,
thank you very much.
Professor Fujita and Pak Dian Sisinggi for the nice discussion. On behalf of committee of this program, we would like to thank to Professor Fujita for nice and useful knowledge about Typhoon MORAKOT and all participants for joining us today. Hope you have learned and enjoyed this discussion. And see you in the next schedule of discussion for the next Saturday. We are sorry to any mistakes during this event. Thank you for all and wassalamualaikum warahmatullahi wabarakatuh. Before we leave, please switch on a camera because the committee will take some picture. Okay. One, two, three, and more. One, two, and three. Thank you very much for your all attention, and bye-bye.
Terima kasih. Thank you,
Prof. Fujita.
Thank you, Fujita.
Very much.
Have a nice weekend.
Thank you very much. You too.
お疲れ様です、先生。
お疲れ様。じゃあどうもまた来週。
はい。
先生、また来週。
はい。さよなら。
Sayonara.
Terima kasih Bu Aini.
Jamata ya?
Mata Raisa itu apa, Bu?
Mata-mata.
Mata Raisa itu apa?
Matanya Raisu.
Matanya Raisa maksudnya mau. Iya tak?
Wah, ya berarti. Ya sudah di-end aja Bu Evi, nanti tidak karu-karuan. Terima kasih semuanya.
Terima kasih.
Assalamualaikum. Terima kasih Bu Rati.